Again, this is John Bush, and today's talk, it's the eighth talk of a lecture series. Today is on the conceptual model of the Moscow Pullman aquifer systems. It could also be called a summary, because in putting together the final pieces of the model and how our subsurface works, we're going to bring back and re-mention the main keys, the main important parts of our that we talked about in the earlier lectures, and bring them together into a what I call a very, what I think, simplified model that most of us can understand on the basin. And so it's sort of a summary, going over some of the same slides, but we're going to pull those pieces and parts together. First slide here reminding us that the area can be, our subsurface can be divided into different segments as we go from the east sides, a very sediment-rich, sediment-thick aquifer. As we go into the central part between Moscow and Pullman, the sediments play a minor part, and the aquifer systems are primarily a stack of horizontal basalt flows on top of each other. And then we over to segment C, starting in Pullman. The aquifer rocks get somewhat tilted and folded, and then they slope out to the west into the Union Frac Creek area, which I call segment C. So most of the talk will do this east to west. We don't want to forget that the Palouse area to the north could actually be called segment D. We'll primarily be talking east to west, and we're primarily going to focus on the lower aquifer, which is we get our water right now at the present time. We're getting all of our water, our municipal water, from the lower aquifer, and most of that water is coming from the R2 Grand Ronde basalts that producing probably about 80% or total supply. There are some wells that get down below that, but for the most part, our lower aquifer supply is, as I pointed out before, is coming from this R2 zone. It is a talk primarily about the lower aquifer, but let's don't forget this low flow up here. That's sort of a key. It's in the upper aquifer system, but that flow is a aquitard to vertical movement of water, recharging water down into the lower system. And the only place that, two places that that may differ is if you look north of Moscow and northeast of Moscow, the low doesn't reach all the impermeable basement rocks. So you have an area up here, which I've called the slopes of Moscow Mountain. That area is, the low doesn't underlie it. So a potential, it is a recharge area. And if we jump over to Pullman, not very clear on this diagram, but in Pullman, the Paradise Creek, and particularly the South Fork of the Palouse, erodes down into the lower part of the upper aquifer and into the upper part of the lower aquifer. So we have two possible recharge areas, one over here in Pullman, and of course off the slopes on the eastern side. Before we get started, just one thing we want to remind you at is, why do we doing all this study, and why, when I talk about significant modern recharge, why are we worried? Well, let's look at this water level chart put together by Steve Robuchon. He puts together charts for wells in the PBAC monitoring system every year. And if we look back here to 2006, we're approximately, our water levels were 2,252 feet, a fairly consistent decline, under 1 foot a year. Getting down here to last year, or 2022, and we have a water level of approximately 2,038. So we've had this fairly consistent decline. If you look at it and analyze the details, you can see that there may be a decrease in the amount of decline over the years, but it's this decline which has us concerned. So that's why, even though I will say significant recharge, we'll talk about modern recharge, there is still a continued decline of our water level from year to year in the lower aquifer. This well is a lower aquifer well. Some of the topics we're going to cover is a very short mention of drainage patterns, remind us of where the upper and lower aquifer boundaries are, remind us of where the Moscow-Pullman Basin versus Palouse Basin, a statement about the emplacement of basalt flows. Primarily, the last 15, 20 minutes of the talk will be tracing the groundwater from east to west in a cross-sectional view, and then we will look at an overview of groundwater flow directions in an aerial view, and that will be sort of a summary of how our model works. Let's don't forget how the model was put together. One of the questions that people ask all the time is, why can't we just calculate how much water we have? Well, what's been difficult is no one discipline has been able to produce a model that has worked or has been able to predict how much water we actually have. So this model, because the subsurface is so complex, this model pulled together lots of disciplines, not just hydrology. It is focused a bit on geology because that's my background. It follows the kind of concept that used by oil companies. Lots of disciplines studied, boil it down, put those keys from each one of those disciplines and put those keys in together as a conceptual model. If you've had the fortitude and strength to listen to all the lectures, I believe you could put one of our cross sections up and go back to, I'm sure you took copious notes, but go back to look at the other lectures and put the keys on that cross section, and you could come up with this model. I'm going to put the model together for us. Let's don't forget that just because I'm doing the talking and I act like I'm the only one that's ever did this, that the information, it comes from a lot of publications, a lot of discussions, not always just a referee journal from reports, student presentations. These are just some of the people down through the last 50 years that have jogged something in my mind that stayed in my mind. So lots of people have worked on this. It's lots of pieces and parts, not only from different disciplines, but also from different people, drillers, PBAC members, hydrologists, geohydrologists, and geologists, and surface people, soils people, and so forth. At the present time, I want to thank Steve Robuchon from PBAC and my wife, Pamela Dunlap, and colleague for being the last two people I've worked over the last couple of years, thinking about the basin. And so let's just remember, lots of people involved, not just me. We get back here and look at the old first diagram introduced, I think, in the second lecture, the outline of what we call the Palouse Basin Aquifer System. Remember that this is not a geographic name nor a geologic name. The geologic name for part of the area, and I use, is this, what I say about the Moscow-Pullman Basin. That is a geologic name. It's an area of younger rocks surrounded by older rocks, and I draw the western boundary right through Pullman. We go along the basement rocks, which are impermeable, and instead of going up into the Palouse Basin, I draw it across between the basement rocks, bring it around to the Moscow area and on around. That's a sort of an internal basin, primarily surrounded by older rocks which rise in a higher elevation. Excuse me, give me a swig of water. can use this same diagram to illustrate a recharge. Our studies have shown that there's a significant amount of recharge coming off of the Moscow Mountain area, primarily because it's steep contacts, high elevation, high snow melt, high rainfall, and it's the primary area that we've identified as a recharge area. Another recharge area identified over in Pullman, where the South Fork of the Palouse cuts into across the interflow zone of the upper aquifer and lower aquifer. So there's expected to be recharge in the western part of Pullman and down northwest into Albia. In terms of other areas of recharge, they're not going to be as significant as that coming off of the Moscow Mountain area. These areas in Kemiak Butte and Smoot Hill, which are quartzites, first of all, lower elevations, less rainfall. These areas around up into the Palouse area surely are providing some recharge, but possibly not, well, I expect not near as much, because the granites area along Moscow Mountain have deep weathered soils along with the high elevation. In the areas around the Palouse City area, they're what we call quartzites and argillites that are not capable of retaining the water, thin soil profiles on the mountaintops and high lower elevation. So some recharge could be coming through there, but not, well, I don't expect a lot. We get down here to way down to the Snake River. And as we mentioned, there's potential recharge moving away from the Snake River. We've mentioned many times the water is not coming out, the groundwater is not coming out into the Snake River. Some recharge has been identified potentially from the water moving from the Snake River towards and into the Union Flat Creek. Possibly some recharge coming off of the southern part of the Moscow-Pullman Basin. Those granites are not near as high as those of Moscow Mountain. Could be some recharge there, not enough data to say that there is. Once again, a low area of recharge, but there are other areas, but we're going to talk about our model primarily as if the major recharge is coming from the Moscow Mountain, and then we'll tie in some recharge over in the Pullman area. Once again, the Palouse Basin, as we define it, is a hydrological term for the lower aquifer, where the lower aquifer is interconnected, similar water levels over a large area, and it's larger than the Moscow-Pullman Basin itself. Sometimes the reason I refer to just the Moscow-Pullman Basin, that's where most of our data comes from. So when we go outside that and talk about the Palouse City area or the Union Flat Creek area, less data, and therefore maybe a little more estimation and not enough data to be absolute in every case. But the central part of the area is where we do our thinking from, and remind ourselves of the origin of the basalts and the location of our basin. I think I sometimes need to be reminded that we're really just a little piece over here on the edge of the Columbia River Plateau. We're a small basin, but unique in the fact that it was a steep pre-basalt paleo canyon filled with a thick sequence over 2,700 feet minimum of basalts and sediments, filled in a very short time against a very high mountain range. So the contact between the mountain range and the filled in aquifer rocks, very, very steep. And if you look around, at least on the northern end of our Columbia River Plateau and sort of the eastern end down into Moscow, it's unique in the fact that we are presently, our aquifer system is very close to high elevation, older impermeable rocks. You want to remember that the flows we're talking about flowed into the area, about 25 flows that came in and blocked the drainages. Just 25 flows out of the 300 plus flows that filled the entire area. So we are unique in the location that we are and unique in one other part. Because we were so close to mountain fronts, instead of forming lakes, there was a lot of drainages formed. Alluvial fan streams, braided streams, braided type channels, maybe even meandering streams. This differs a little bit from other areas where there tends to be a lot of lake sediments and more clay. We have some possible lake sediments in Moscow, but most of them are alluvial sediments producing the possibility, well, not the possibility, producing the fact that we have about 25 to 30% sands in our subsurface, and that differs a lot from the other areas around. This diagram we see many times just to remind us that the upper aquifer, lower aquifer contact occurs approximately at the top of the uppermost Grand Ron flow. In Moscow, that uppermost flow is farther down in the section, therefore different vantage sediments. The upper aquifer and the lower aquifer have one characteristic in common, and that is the fact that most of the water, particularly on the eastern side, comes from the sediments, not the basalts. Here's this low flow I've talked about, which covers the whole area, and the data now shows that water can be traceable from this area towards the mountain front on the Moscow mountain slopes. Water can be traced from there into Moscow, into Pullman, and in the upper aquifer. That water has to be coming laterally from the northeast of Moscow. So that particular mechanism of recharge is the same mechanism we're going to talk about or discuss for how the water is getting down into the lower aquifer system. Remember that, how does that recharge work in the mountain areas? We looked at some slides of alluvial fans. This is in the Death Valley area, but it shows these nice defined channels, numerous channels coming out from the front of the mountain. Alluvial fans form when there is too much sediment in the water, in the surface water, and as they reach a sudden change in base level, in other words, when they come out of high gradient areas into low gradient areas, they drop those sediments to the alluvial fans. Those alluvial fans have many channels. So the idea here is that the water is getting into the system up in the mountains and getting into the subsurface through alluvial fans. Now this, we have somewhat buried. My estimate is we have over 100 alluvial fans, minimal 100 alluvial fans complexes buried and along the mountain slopes between the lower elevation basalts and the higher elevation granites. Remember those streams coming out the mountains will sometimes go along the mountain front. Sometimes they will shoot out front. But the point is every alluvial fan had numerous channels zigzagging across at any one time. I would assume and theorize, and I believe the model is correct, that there's over 100,000 channels zigzagging around in the subsurface of the Moscow mountain slopes. Those areas have the sand in the channels. The sand is transmitting the water laterally or downward towards the west. And towards the west, we have something like this situation from up in Alaska, where the alluvial fans comes down to the end and comes down where the terminus is here. And along the edges, you have a lot of braided streams, meandering streams, primarily braided streams. This can be documented in our area very easily because our sediments have, our sediment areas have what can be identified from the nature of the sediments as being poorly sorted, rapidly deposited, channel deposits of coarse grain, sand, minor gravel, and occasionally some granules. But coarse grain, intermixing channels, and once again, thousands of channels, and this situation would have been created 25 times for the whole Moscow-Pullman Basin, 10 times for where we get most of our water from, which is the R2. So in our model, we have our water coming down off the mountain front from the Louisville fans, getting into the stream channels that were deposited along the edges of the basalt flows. And now the next question is, how does this water get over to Pullman? How does this water even get down into Moscow when east of Moscow, excuse me, the granites aren't that high, the elevation of the granites are not that high, and the low flow in some places goes right up against the basement rocks. Our water has to get from our recharge data. How does it get from these areas? In our case, we can think of this being Moscow Mountain. How does it get down through these fans? It's down into these channels. And the next question is, how does it get into the basalt flows? So we look at a cross-section we looked at before. This cross-section turns a little bit to the northeast. The Pullman test well is out here on the west. Washington, Idaho boundary here. Up in the very top right, you may not be able to see because of the picture, but you're going up to the Eilers Gulch, end of the Eilers Gulch Road, about 2,900 feet. And this is both a conceptual diagram, but it's based on good downhole data from the wells. And once again, we can see this basalt flow in my mind, along with a thin vantage out here to the west. It produces its aquitard. So we're talking the water gets down into either channels or debris flows. Debris flows are very coarse. My drawing shows them over here just plastered against the granite areas. By the way, for those who are listening for the first time, we've given the references for this data in previous talks. So I'm going to bypass providing the names where the research comes from. If you want to check on any of this research, go to Bush 2022 on PBAC's page, PBAC's webpage. There's a summary of the last 40 presentations, reports on the PBAC page. You can look at those and find specific titles. The recharge has been documented to be coming down this area off the Moscow Mountain slopes, getting into and underneath into the vantage in the upper aquifer. The upper aquifer is definitely proven to be modern rechargeable water. We also now have evidence that the water getting into the lower aquifer system is modern water. If you're interested in the determination of why the carbon-14 dates are misleading, look back at the recharge lecture, and you'll find out it's been determined that those carbon-14 dates are much too old. So there's modern water getting down into this part. How do we get it over to Pullman? How do we get it into Moscow? In this case, if we've turned the cross-section a little bit to the northeast, water is maybe moving laterally. It's probably moving laterally down into Moscow. So we're now turned up to the northeast. Just envision it getting down into the Moscow area. To the west, how do we get it over to Pullman? How do we get it over into Washington? Well, we've talked about before these thin flows, these flows that have pinched out from the west. They have fractures on the top and the bottom, which join each other and make very high permeable units and very high areas of storage capacities. Lots of evidence pointing to this all across the Columbia River Plateau. So what I surmise is the water coming out of the sand channels, when they're in contact with the ends of these basalt flows or in contact with a thin flow. For example, over here, this Grouse Creek member, very thin, it's got to be carrying, it has the potential for to carry a lot more water than the dense parts of the other flows. Studies show that when you look at various hydrological parameters of the basalt, it has a wide range and of very low hydrological parameters to very high parameters. These pinch out zones have the highest hydrological parameters, whereas the dense portions of the flows have lower hydrological parameters. So the water is, in my mind, and in putting together the model together, water is getting where the sand becomes in contact with a thin flow or a terminus. The water is getting into these flows where it's highly concentrated on the thin ends. And we have talked about some wells in Moscow, which look like they're basalt wells. That's because they were designed to get the water, designed to tap the resources out of the thin flows, mainly because that's much more efficient in terms of cost. It's very difficult and very expensive to have the proper screens to get the water out of the sediments. So they look like basalt wells. They're really getting their water from the sediments that's transmitting it into those flows, and then the water is moving west. So the next part of our model is, how do we get the water to move from Idaho into the basalts and across the 7-mile area into the eastern side of Pullman? Well, the way that we think, the way that that's happening is that the water, once we get into the thin zones, is getting into the interflow zones of the central area of the Moscow-Pullman Basin and is moving towards Pullman in these interflow zones, which we pointed out make up about 20% of any one flow. So in a sequence of basalts, it's basically 80% impermeable areas versus relatively impermeable areas versus the zones where the water is. 20% of it is the water moving through these interflow zones. So how is that happening out here in the, gotta get down here and find stuff. How is that happening in the central part of the area? We don't have any production wells out there, but we have enough data to show that the layers, or the basalt layers, are very horizontal. Here's a cross, and instead of going east-west this time, we're going north from the south to the north. The south over here on the right, the Pullman test well, going north close to 9 miles up to the Butte Gap well, where we have some data. What's amazing is the contacts identified there using basalt chip chemistry. This little Grouse Creek flow, the top of that flow, nearly the same elevation down to the south. The Pullman test well, amazing horizontal contacts. When you look at our lower aquifer wells, numerous ones that are being drilled here in the last 2 decades for domestic water, when you look at those logs and interpret them, the drill reports, you'll see that the intraflow zones are very well developed, and you can oftentimes correlate from one well to the next because they're so well developed and easily identified by some of the drillers, not all of the drillers. One driller doesn't mention scoria or permeability differences or fractures, but what he does note, he'll list X feet of soft basalt, X feet of hard basalt. So you can go to those logs and it comes up with the same number, or approximately the same number we've been talking about 20%. The soft areas are the intraflow zones. So about 20% made up of intraflow zones, about 80% made up of hard basalt, which are the dense centers. And you can take his logs and correlate them to other drill logs, and oftentimes just trade horizontal contacts, 1, 2, 3, 4 miles. So this area in the central part of the Moscow-Pullman Basin. The water is now into the intraflow zones, and it's moving somewhere to the west. And remember, we have documented that we can trace this water from Moscow Mountain over into the Pullman area. So it's moving across those contact zones. And what happens when we get to Pullman, however, is that some things change. And let me move my charts up over here. We can look at the surface drainage, and we notice easily most of the drainages are trying to be east-west, trying to flow out of what we call Moscow-Pullman Basin. But when we get to Pullman and Albion, we see our drainages now are going to the northwest. This is because the rocks in a larger feature are in a structural block where they dip gently to the northwest. And that has been shown to be the cause for why the water, part of the reason the water moves away from the Snake River. So if the contention here is if the water is, subsurface water is moving the same as the surface water, it's going to change about Pullman area. And that's what little data we have, it shows that it's doing just that, moving to the northwest. The unfortunate part is that out here in uniflactic areas, we don't have any production wells. So we have to look at the data on the folds that may be also helping to cause the water to move the northwest. And this diagram illustrates identified folds, particularly the Pullman anticline here is very well proven. It's a small anticline, but it's the largest one in this area. That is paralleled by a syncline on the east and a syncline on the west. The Union Flat Creek syncline met many years ago is causing the Union Flat Creek primarily to fall along the center of that fold. So these features, as shown across the Columbia River Plateau, have the potential of being barriers to lateral flow. And that's what I think is happening. We start to get a barrier to east-west flow, and these folds are creating water in the subsurface to move to the northwest. At the same time, I think they are slowing down that movement. If we look at the overall elevations in the transition between the segment B and segment C, we find out in the Albion area, there's about a 9 to 10 square mile area to where the elevations are much lower, 100 feet or more lower than they are in the Moscow Pullman area. So the idea is that the water is coming into the Pullman area, meets these structures, each of which have the potential for being a barrier to lateral flow. And as we recall, water moves downhill, down the intraflow zones. So this area up here is sort of the sink in my mind, and that's where the water is moving towards. And then we have information that, or documentation actually, pretty good documentation, suggesting that there is recharge along the south fork of the Palouse where it cuts down into the upper Grand Ronde. And we have documentation that the water is moving from the northeast to the southwest. So water comes across, being forced to move to the northwest, and then as we reach these lower elevations up here, the water then is going to go down the slopes, documented slope of about 200-foot drop out into the Uniflat Creek area, hits this northwest syncline in the northwest dipping block, and then is forced to move to the northwest. If we look at a summary, let's look at the summary in an east-west direction, and we can summarize a lot of things on this diagram. This is the diagram that's in several publications. One part that's misleading is in the Moscow area, as illustrated here, the low flow does possibly sit right against the granites. But remember, we turned the cross section to the northeast, and we see that recharge water is getting into the vantage member, laterally moved through sand lenses and layers. So we get the water into the vantage member and into the sediments of Moscow. These waters in the lower aquifer are going over into pinch outs and moving westward. There seems to be some kind of reason why the upper aquifer is separated from the lower aquifer when they both have the same mechanism for being recharged. There's probably a saprolite soil somewhere that reaches some of the, that separates some of the earlier fans from the later fans, and therefore they get a little bit separated enough to create water differences. But the connection, the same thing for both aquifers. So water is coming down into the sediments and moving in this case for the lower aquifer, it's moving in across interflow contacts, across segment B, gets over into Pullman, and a cross-sectional view. We see these little folds as we talked about the water now coming up against the barriers. Some other potential barriers are northwest trending dikes, possible small faults. When we look at the Pullman area, we can talk a little bit more about how this aquifer system works. There are 5 wells presently being operated between WSU and the city of Pullman. Those wells from the reports show that they hit water in the interflow zones as the well was deepened, but the major aquifer was at the base of those wells, except for WSU 7, which we talked about being a research well. But the production zone, the production levels are all from this sediment zone down at the bottom of each of those wells. They didn't extend them any farther because they hit enough water by then to produce 2,000 to 3,000 gallons a minute. The upper part of those wells tell us that water is coming from the interflow zones. You can trace those interflow zones right into the central part. However, these sediments indicate another possible source or another mechanism by which the water is moving through our aquifer system. Excuse me. These sediments here are pillow lavas, gravels, one well, WSU 8, water is coming entirely from a gravel interval. Those are the paleo sediments deposited from the Paleo Palouse River, which one time flowed from the Palouse City down to Pullman. That layer, that old channels could be either bringing water from Palouse City, or it could also be a collector unit for waters that started to move from the sediment area into the basalts. But it's creates what I call sort of a composite wells. And once again points out the fact that if you calculate these as a basalt aquifer from top to bottom, you're going to get incorrect numbers because it is both a basalt aquifer system and a sediment system. And from what comparisons I could make, I would say that 3/4 of the volume of the water drawn out of those wells is coming from that sediment zone. So in my mind, not necessarily proven by data, just by comparison between well to well, primarily the fact Pullman 5 is cased all the way to this zone, produces 1,700 gallons a minute. The other wells produce about between 2,000 and 3,000. So in my mind, that's indicating that the lower the sands, the sediments are producing about 3/4 of the production there. So now what happens is we hit these these folds, and we have to deal with this slope that goes all, excuse me, get my cursor in the right place here, have to deal with this slope that's putting the interflow zones out to the west. So these interflow zones are dipping in general to the west, but they're also, and we've talked about this before, they're also plunging to the northwest, sloping to the northwest. So the water's got to get down this slope out here west of Pullman. How does it do that? And how are these wells that show similar water levels connected to the Moscow-Pullman Basin? Some people would say, well, the water levels are similar, so therefore the water is just flowing out through Pullman out into the Flat Creek area. I don't think it quite works that way. The fact that they are similar water levels tells us that they're connected to the Moscow-Pullman Basin. It helps define what we call the hydrological basin, what we call the Palouse Basin. But the fact that two wells have similar water levels does not tell us anything about the nature of the connection. There are 3 or more pump test type theses that were done and sponsored by PBAC that show us the lower aquifer, even though it's interconnected across a large area, it's very compartmentalized. So one area of those compartments is not necessarily connected the same to other compartments. So I would contend that as the water gets into Pullman, it moves towards this low area, and what I call sneaks around the lower end of those folds, or what we call plunge, and then works its way, as been documented, it's moving along and down the slope of the Pullman anticline to get into the Union Flat Creek area. The evidence is circumstantial, but it's extensive that these area out here, either as a group or as one individual structure, is a barrier to westward flow, to southwestward flow. So you can look at that as a large area of a barrier zone, or you can look at any one feature creating the barrier. But the evidence is, even though we don't have a pumping well out there to prove that, this area slows down the water movement and probably forces the discharge to be in a very small area up here between Union Flat Creek and Colfax. So the water is restricted, gone through Albion, explaining why the earlier wells were under confinement. Water was being held back. It had these huge artesian wells pumping 2,000 gallons a minute or more because the water was not moving through that area evenly. It's limited to a small area. Water was moving, held back by these barriers. And then as you got out to the west by flowing along interflow contacts on the western limb of the anticline, and then getting down into the Union Flat Creek area. So if we look at the lateral view, a map view of how the water is moving, this is for our lower aquifer system primarily. The blue arrows, we've shown these before, indicate the expected primary movement of the water in the subsurface. In some places it could be documented, like off of these slopes coming along the western end of the Pullman anticline. This big arrow here going down Union Flat Creek, it's almost one of those things that has to be moving down there because we can document it as coming away from the anticlinal slope next to the Snake River. So some of these can be documented and some are extrapolated from our knowledge of the structures. Over to the east, the primary source of recharge coming off the Moscow-Pullman area. Possibly I should have had some arrows on here indicating that some of it's getting down into Moscow, then moving west. These waters moving west run into the Pullman anticline, run into the syncline, and is being forced to move towards the Albion area, and then eventually around, as we've talked about, around the Albion area into the Union Flat Creek area. Looking outside or looking at another component of our basin, I have the arrow going both ways up here into Palouse City, primarily because it can be documented that the water going across there, there's at least a minimum of 600 feet of preliminary basalts that goes across that gap. The water level data tells they are connected. But once again, I do not know the nature of the connection. It seems to be pretty good because the Palouse Gap well, the Butte Gap well, sort of mimics the well in Palouse City area. So the connection might be pretty good, but don't know which way the water is moving. The reason, one, is that the upper Grand Ronde surface in Palouse is just a little bit lower than those down in the Moscow-Pullman Basin, suggesting the waters would be going into Palouse City. At the same time, we know that the Palouse River, and early on in the stages of the development of the aquifer system, flowed from Palouse down into Pullman. So there probably are some buried channels of the ancient Palouse River causing water to move down from Pullman, from the Palouse city into the Moscow-Pullman area. So the arrow has to be both ways there unless we get some documentation. In either way, the water, this area up here in the city of Palouse is connected. I think that it's being controlled primarily by these low elevation interflow zones in the Albion area. We have evidence saying that the groundwater in one case is maybe not be following the drainage. Lots of clay here in what we call the 4 Mile Gap, a very small gap. We don't think the water is moving across there. Well data west of there, lower aquifer wells west of there have very little water. So lots of clay have been documented in this area between the interflow zones and the quartzites of the basement rocks and between the interflow zones of the upper and lower aquifer. So I think the primary movement is along this front of the Smoot Hill. That might be, maybe I should have had a question on that. Data shows that the water is probably moving down a dip slope away from the mountain areas, away from the quartzite areas in the Koufax, and the Koufax is on a southwest, excuse me, dipping block, and that water is moving out into the southwest and probably not connected in any significant way to the Palouse Basin. So this aerial distribution versus the lateral distribution, one can expect which way the water is moving, and our resources as they're coming from, particularly for our resources in the lower aquifer system. This model is relatively simple to think with. Remember that it's a model, it's a framework for thinking. You should question it and test it. Any part of it that you're interested in or have done research in or thinking in, whether it's surface water, whatever, the model is a framework for thinking. Until it's been tested and predicts, the model has to be either modified or abandoned. A lot of people forget that a model is to help thinking, is not always accurate. And that goes the same for a numerical model. I think the model I presented here will help any researcher focus on their area of study. I think it will help a person just interested in the aquifer system, trying to understand how it works, wanting to read some of the academic and consulting reports. I think if you understand this model in general, it will help you question it and test it. Since I've thrown that challenge out there, there is one more lecture, lecture 9, in which I will take some of my thinking and some of my findings and put it into the model and see how well that model works. Answer some of the questions that have come up during these, in my mind. Some of these questions also from Steve Robichon, some of these questions about the model or information that I put out. So I'm going to, in the next lecture, try to question my own model. I think at the present time, I'm very confident this model will take the test of time. Some previous models we've had, both numerical and qualitative models like this one, have not been verified through time. They've actually showed that they were there was too many problems with them. I think this model will last the test of time. That's bragging a little bit. And I'd like to thank you for all your time you've spent. It says here, thank you for the opportunity to speak today, but also thank you for, if you had the perseverance to go through the previous lecture, thank you for listening. And I hope I've helped you understand the subsurface, understand our aquifer systems, and will increase your understanding of the ability for any kind of future information that comes about. Thank you very much.